Now, the generalized gamma distribution was not a distribution that was studied during this course, so we embarked on some further research and we found that the generalized gamma distribution has the ability to mimic attributes of other distributions, such as Weibull, log normal, and again, this is determined by which distribution it mimics is determined by the values of the distribution parameters for the G-gamma distribution. The reliability function is described below. We can see that in the case of lambda greater than 0, we have a distribution that closely mimics a Weibull distribution. If lambda is equal to 0, we have a distribution that closely mimics the log normal distribution. And again, if lambda is less than 0, we have purely a gamma distribution. So in order to aid us in being able to evaluate this distribution further, we made some constraints. The constraint that we made is that lambda could not be less than 0. So therefore, when we do this, we see that in the case of this unscreened population that we're analyzing, it would be best described by a log normal distribution, since lambda in this case is negative 45.69. Again, by making the constraint that lambda cannot be less than 0, then the next best fit is a log normal distribution. So again, our chi-squared goodness of fit test was correct in rejecting a pure fit to the log normal, but since we are making a constraint on the G-gamma, we find that the best distribution to describe this failure mode is a log normal distribution. Again, this goes to show us that in real-world applications, determining the distribution that a particular failure mode follows can be quite a difficult task and may involve us taking and making assumptions on the data to get us into a easily handled lifetime distribution. And in this case, that is exactly what we're doing. We're going to take the data, we're going to make this the constraint on the lambda value of the G-gamma distribution, thus making or forcing the distribution to be a log normal lifetime distribution, allowing us to apply techniques that we use in class. Once we have determined the distribution that we're going to follow, we use Weibull++ to determine the parameter estimations. In this case, for the unscreened distribution parameters, we can see that we used the MLE methodology. We had a confidence in limits of lower 5%, upper 95%, and we also have a two-sided Fisher matrix confidence level of 90%. The parameters for the mean was our T50, basically is 29.24, the lower limit of 28.05, and an upper limit of 30.4. For the standard deviation, we can see that the estimate is 5.99, the lower limit of 5.64, and upper limit of 6.37. We conducted a similar analysis on the screened distribution to determine the parameters under investigation here, using the same confidence level limits and methodology. We determined that the T50 for this particular data set is 28.04 with a lower limit of 27.13 and an upper limit of 28.95. The standard deviation of 5.56, a lower limit of 5.29, and an upper limit of 5.85. Also with this data set, we wanted to determine if a defect subpopulation existed within this set of data for both the unscreened and screened population. The reason why we suspect that a defect subpopulation does exist is that relative to the number of parts in the field, we have a very small failure rate. For instance, in the unscreened case, we have roughly 800,000 units in the field and roughly 645 units that have failed. So therefore, we believe that a defect subpopulation may exist. So to conduct this analysis, we use graphical techniques to start off with. The first thing we did is to basically take the population as a whole, or to take the population with a p equal to 1, and plot that data on a log-log scale with the CDF with the cumulative failure rate versus time in hours. And what we can see here is that the data set for this, which is displayed on the graph on the left, has some slight curvature, indicating that a subpopulation may exist. Our next step was to take this data and to evaluate it with a p equal to 0.006. Again, using the same plotting methodologies, plotting the cumulative failures over time and on a log-log scale. Again, if a defect subpopulation does exist, we would expect to see a much more linear plot. And what we see here on the right-hand side is that it is very strongly suspected that a defect subpopulation does exist by the fact that the replotted data with p equals 0.006 is much more linear than that with p equal to 1. We conducted a similar graphical analysis on the on the screened population with p equal 1 and p equal 0.008. We can see here on the graph on the left that with p equal 1 we have some significant curvature to the graph, again suggesting that a defect subpopulation does exist. Furthermore, we found that when we replotted the data with p equal to 0.0008, that the data does become much more linear than that with p equal to 1. Again, strongly suggesting that a defect subpopulation does exist.